Welcome to the second session, and we're pleased to have Iain, who's no stranger to us, to these presentations, and so it's carrying on a theme of developing new ways of tracking satellites, new ways of receiving telemetry, new ways of using our opportunities in space to explore all sorts of new features. So without much more, I don't think Iain really needs much introduction. We've known him for many years, and so over to you, Iain. Tell us all about it.
Okay, right. This presentation is strongly based off one I did in 2018, but has been updated to remove some obsolete material, and there is some new material that I added. So I'm going to cover automating the reception of FUNcube, telemetry, weather satellite pictures using GNU Radio. Okay, we'll do it the old-fashioned way. So, as I said, we're going to cover station software and hardware. We're going to cover how you receive FUNcube, how you would receive APRS packets, mainly from the ISS, and how we would recover weather satellite pictures. And then we'll have a quick wrap-up at the end. So, for the hardware, FUNcube antenna, a turnstile, a wideband amplifier, a splitter. Now, what do we use the splitter for? To feed an extra pi from the same antenna, so we can do two things at once. FUNcube Dongle Pro Plus is the hardware, although you could use a RTL dongle as well. Raspberry Pi 3, it's only a 3. GNU Radio for the software, and APRS FUNcube telemetry decoder. So, how do we go about receiving the FUNcube satellite? Well, in the digital world, you still have to do exactly the same thing as you do in the analog world. First thing is you've got to acquire the signal. Then you've got to tune it, filter it. Since we're talking about telemetry here, this thing got to be formatted, decoded, and then, if you wish, uploaded to the data warehouse. So how do we do all these things? How do we acquire the signal? In GNU Radio, we have a concept called blocks. And in this case, we have a specific block that allows GNU Radio to talk to the FUNcube Dongle Pro Plus. It has a bandwidth of 192 kilohertz. If we tune to 145.9, we get all of the 2 meter subband except 4 kilohertz at the very top. So pretty much the whole thing. Now we've acquired it, we need to tune it. How do we do this in GNU Radio? There is a block called a frequency translating fur filter. Now, a lot of you might not know what that is. I know you do, Martin. I know Heather does. See it as the big fat tuning knob in the middle of your rig. That's a very simplistic way to put it, but it's also the simplest. Okay? And then, so that will then tune it to the beacon frequency. If you notice, the center frequency is not an absolute frequency. It is an offset within the 192 kilohertz. So that is one big difference between the digital world and the analog world when you're dealing in baseband. Also shown on screen is a rational resampler. I'll explain a bit more about that later on, but effectively what we do is divide it down so that we don't have so much bandwidth to process later. Now, since we have Doppler, we have to deal with it. Luckily, GNU Radio has a block that allows us to control the flow graph, as we call it, remotely. So I wrote a script that once a second calculates the Doppler shift by talking to a satellite protection program. I actually use predict. That sends the information to the flow graph, and then it adjusts for Doppler. This lets us get more telemetry packets down, and you get a nice straight line on the waterfall rather than a wavy one, or sloping one, I should say. Now we're actually ready to actually filter and resample. Yeah, we want to filter it so that we've got the largest signal to noise within the filter possible. But we also need to resample it down to 96 kilohertz, because that's what Alex's decoder requires. So we resample it, it's the same resampler you saw on a previous slide, and we pass that through a low pass filter. I chose about 4K bandwidth because I found that was the most useful from a computational perspective, but also takes account of any residual Doppler and also gives us the largest signal to noise ratio while still, you know, permitting the beacon within the bandpass. So we've now got our nice clean signal of 4 kilohertz bandwidth. The decoder also, so we've now got to format the signal properly for the decoder. The decoder requires the signal to be mixed in with a 5 kilohertz signal to shift it up 5 kilohertz in the spectrum. It also requires the data in a particular format, so I'm not going to go too much into this on this slide, but essentially we mix in a 5 kilohertz signal to shift it up 5 kilohertz. We multiply it by 48K, and then we change it to a different digital format and then send it on to the decoders themselves. Yeah, I'm not going to get too much into that because that's all very geeky and techy. We're at this point here, where these yellow connectors are, we are well and truly out of the RF spectrum and into the computational world. Here is the entire signal chain. And as you can see, it's actually not that many blocks. So I just left that one in for completion. Yeah, this software is available. Like Martin, I'm all for open source. So if anybody wants a hand, this was built with a GUI anyway. So you can actually install the new radio, take these slides and create your own. Yeah. Just a little bit on Alex's decoder. It listens to a UDP port, so you need a little bit more Unix plumbing. Two utilities you can use there, SOCAT or NetCat. It decodes the telemetry packets, and then pipes into a shell script that uploads them to the FUNcube warehouse. Yeah, there is a newer development here, and this is part of the slides here have been updated. There's a decoder built into geosatellites, which is better, and Alex will tell you that himself, which helps simplify some of the signal chain, because you don't have to do all those digital conversions I spoke about. Now, what if we want multiple receivers? Well, whereas using an analog splitter can be done, as we all know, that's a 3 dB signal loss. However, in the digital world, you can split as many times as you like and not lose any signal once you've acquired it. So here we have the signal acquisition. It's the same block you saw before. But if you note, I send that signal to two separate frequency translating FUR filters, or two big tuning knobs. Yeah? If you look carefully, you'll see they're on different frequencies. So this, back in the day, was allowing me to receive multiple FUNcube spacecraft at the same time and just leave it running. So, and obviously not shown here is two rest of the chains. So that's FUNcube. Before I go on to the other spacecraft I'm going to talk about, any questions? Because I know it's a lot to take in. Okay. APRS. They're all on the same frequency. So there's only one extra signal chain required. A center frequency of -75 kilohertz or 145.9 will get you on the right frequency for the FUR filter. You need a software CNC. There are plenty out there. Direwolf, the old Linux sound modem, and all the rest of them. Direwolf is probably the favorite these days. But we also need a sound card. So how do we do that in GNU Radio? Now, you actually need a linear receiver, yeah? It needs a sound card, as I said, but actually you send audio out to the sound card. So you need a way to get it into your software decoder. So you need a virtual audio cable, or in Linux, you might use Jack D. So what do we have here? This is the full receive chain for APRS. We've got the FUR filter again. Yeah, we've got a low pass filter. We then have to convert it from an IQ stream to something the sound card could understand. And we call that real. Yeah. We then resample it down to the sample size of the sound card. We multiply it by a constant to get an amplification and send it out to the sound card. On the other side of that sound card, there's the virtual audio cable, which you then connect to your software decoder. So far, on a single Pi 3, decode the entire telemetry from the entire FUNcube fleet, however many are still transmitting telemetry. You can receive APRS packets from the entire APRS fleet. But hang on a minute, weather satellites aren't too far away, are they? So what about them? They are on a slightly different frequency, but they're within the dongle's frequency range. Tip here, there's little known limitation with the new radio FUNcube and RTL drivers. Yeah? Once you set their frequency at program startup, you can't change it without stopping and restarting. Yeah? So, need a second Pi and dongle in order to do weather satellites as well. Now, we are explicitly talking about the weather satellites on 137 megahertz-ish. I'm not going to deal with the stuff up at L-band that needs a steerable dish. Yeah. So there are two main types: the NOAA APT fleet, which has been going for donkey's years, and the Russian Meteor M2.X fleet. I think they're up to 2.3 now. They've had a couple of incidents with a couple of them in different ways. One failed on launch, one went rather loopy on orbit. Again, frequencies are spread across the entire band. It's larger than 192 kilohertz, but the signals themselves are small enough bandwidth to pass through 192 K. So, again, first thing we've got to do is acquire the signal. So, when I designed this, we have a separate flow graph for each spacecraft, because as I said, once you set the frequency, you can't change it. I have a script that runs at midnight, gets all the passes, excludes those that don't get above a certain elevation, because if a 2-degree pass is pointless. Yeah, sets the priorities, and schedules each flow graph to stop and end, so that the next one can then set the frequency appropriately. So, how do we decode it? Well, due to the fact that we've got to stop and start, we essentially record the raw data and then process it later, when later means we've stopped recording. So actually, what I actually did was the scheduling script takes care of kicking off anyway. WX2IMG is used for the NOAA spacecraft, but I do have another flow graph, again from Alex, that decodes the raw data as well. Quite interesting comparing the two. But what about the M2 satellites? There is a decoder for the Raspberry Pi and one for the AMD Intel chips. It does work, but it will take hours to process the pass. Thankfully, there's only 2 passes a day, one of those is at night. The Pi 5 will be faster, but I've got to get around to swapping that hardware out. It is on the list, but it's on the get around to it list. It got put on there when Pi 5s were in short supply, on account of that was the limiting factor. Now, the limiting factor is everything else that's going on. So, I've just got a couple of pictures to show you here. That is from NOAA, I think it was 19. As you can clearly identify the UK, and Iceland for that matter, and Europe, but there is interference at the top and the bottom, and some nice dark lines in the middle. That spacecraft goes over at about 11 o'clock in the morning. That's when a whole lot of the pages on 137 megahertz start transmitting in Coventry. Your mileage may vary. This one is from Meteor M2, before that one, or M2.2 I should say, before that one broke. Again, you can clearly identify the UK and Europe. This one, you will see a couple of bars at the top. Yeah? They are actually one of the NOAA spacecraft that's on a very similar frequency, causing the signal to drop out because the Meteor spacecraft uses PSK, QPSK to be precise. So of course you either get it or you don't. Yeah. For some reason, they put the Russians put their spacecraft on a frequency very close to the NOAA one. Now this is, believe it or not, the low resolution. You can still identify the Pyrenees and the fact that they've got snow on them. So that kind of tells you what time of year it was. So that's just really to compare the quality of the two. Bear in mind, it's all on the same hardware. You know, that just shows you the difference between the analog transmission and the digital transmission. Other possibilities, some of which I've done, some of which I haven't. With a HF upverter, you could receive the weather facts from Northwood in Germany. You'd want to use FLDigi with that, but yeah, you just connect FLDigi to your virtual, excuse me, virtual audio cable. You can also receive the DAF text messages on 490 kilohertz and 518 kilohertz in a similar manner, and I have done that. Unfortunately, Northwood can be very weak for me, so I didn't really get to that. Okay, future plans. Well, we heard about 2 potential new FUNcube spacecraft, since they'll use the same telemetry format. That won't be a problem. When AMSAT-NA get their Golf spacecraft going, depending on the telemetry format picked for that, then there's no reason why we couldn't do that. Obviously, there's adding future Meteor spacecraft. That's definitely on the list. There is one planned. You know, add a third pi for weather facts and navtex. I don't know what's gone wrong with that slide because that part of using the GSAT decoder was deleted. Upload weather pictures to a web server. I actually already do, I just don't publish it. And the telemetry values could be sent to our RD tool or something else for graphing, but the truth is we've now got one for warehouse, so there probably isn't much point. So, with that, any questions?
Anyone got to fire away? No. Well, I'd certainly open my eyes to a lot of interesting things that you can do with GNU Radio. I think it's a fascinating tool that allows us to construct digital or pseudo radio components and link them all together in all sorts of different ways. And it's far easier than getting a soldering iron out and trying to design some filters and put some components together. And you know, I think there's it's a toolbox full of all sorts of interesting bits and pieces when you start taking the standard parts of GNU Radio and then adding in the specialist bits that Seth and various other people have written. I think it becomes quite an interesting toolkit that you can then develop all sorts of different radios from.
If I could just add something there. Right, what I would say with GNU Radio, don't try to chew it all at once, take small bites, start easy. You know, all of that was probably 3 to 5 years worth of understanding GNU Radio. Writing those flow graphs, when I came to write them, took me an evening. But it's finding out and understanding the concepts behind it that takes the time. It's a very steep learning curve, you know, but
well, good luck. I mean, that's what we like, isn't it? Steep learning curves and challenges. So,
Hello, Ian. I wonder, how do you start in learning GNU Radio?
That's a good question. Yeah. The first thing, what did I do? I looked around the web, found some examples, and one kind of did what I wanted it to do, and I started fiddling. And then I took it back to first principles. First thing I did was get one of those signal acquisition blocks and connect it to a waterfall. And then I put a filter in and fed that to a separate waterfall. So I work out what it's actually doing. And then I put a resampler in and built it up, built it up, built it up. And so that's how I started, which is actually why I took you through those steps of having the acquisition, then the tuning, then the filtering, then the decoding, because that's exactly how I started and exactly how I built it.
Hi Ian, John, M0IDA.
Hey, John.
Thanks for the presentation. For the willing experimenter, could you just take a step back, please, and describe the initial signal acquisition and what might be a good place to start physically?
Okay. Essentially, SDRs are basically, to simplify it, they're simply big fat ADCs. You can actually use a sound card for VLF stuff. So you will have a dongle which tunes to 2 meters. So you program that dongle to tune to 2 meters, and you get out an IQ stream out of its USB port, and that's how it actually acquires the. Well, that's how you acquire the signal. What it does in hardware, that's black magic.
Hello, Ian.
Hey,
Yes,
John.
so I was going to say one of the better ways also to learn GNU radio is to possibly not do it on a Pi, because they are a little bit gutless. So people have only got laptops to a penny,
Yeah,
and it's a much more pleasant experience than
yeah, that's
being
good.
resource limited.
Yeah, that's a good point John has just made. The truth is, I didn't develop it on a Pi. I ran them on a Pi. Yeah, I've got a dirty, great big machine that was built for GNU radio with 8 gig of RAM and goodness knows how many CPUs, and so I would develop the flow graph on there, then push it over to the Pi, because it's all written in Python. Of course, as long as you've got the libraries installed, then it will run anyway. So yeah, I would not recommend starting GNU Radio on a Pi. Use that for when you want to run something like this autonomously, stuck in the garage once you've actually done the development.
Any more for any more?
You're not allowed to ask questions, are you?
Oh, I'm not going to ask a question. Just to follow on from your answer about the whoever it was asked about how to do it. Recently, in the last year or two, they've really improved the online examples. There is a lot now of tutorials either built in or in the websites for GNU Radio.
Yeah, I guess I started long enough ago.
Yeah, so did I, but
Yeah.
right from your first SDR right through to doing the actual decodes of some of these satellite stuff in manual mode.
All right, another one.
Hi, as a relative novice complete novice to satellite work, is there any reason you're using an SDR with such a low bandwidth? Like you can get 10 megahertz out.
No, I do have some nice USRP devices.
Yeah.
I use those for other things. They're doing it in my QOL 100 station, for example. Yeah, this was done as a small, self-contained, running 24/7 device, and for what it needed, I didn't need 10 meg. I needed 192 kilohertz. Well, 200 would have been perfect, but yeah, I'm not going to worry about that. And so it was meant to be low power, running 24/7, autonomously, stuffed in the garage, connected to the antenna, and I forget about it. I can go do more interesting things with my time.
Yeah, that makes sense. Thanks.
Yeah.
Yeah, I guess it also reduces the amount of processing power. If you've got 10 megahertz worth of data,
Yeah.
that's a bit of a hard cookie to crumble. And
That's
set for a
that's
Raspberry
another
Pi.
good point. If you've got 10 megs, that's great. You've got to process it down. And if you're looking for a 4K signal, what's the point?
Good. Any more? Oh, another one.
I was going to say also, it does mean that you choose the SDR, it's appropriate, as you said, Ian, but you can be looking at receivers or transceivers or whatever else you may want to stick on the end there, and as long as
Yep.
there's a block supported,
Yes.
right,
and-
or you can get it into, say, raw audio or whatever you need, you can just throw it in there, and it gives you and you can basically use most of their, say, the examples shown there by Ian. You use most of those and just change maybe the input or the output block, and you run away. It's
Exactly.
fantastic.
Yeah, and some of this would have been developed on the one of the early USRPs, because that's what I had at the time. But then again, I don't want to waste that running 24/7 when I can buy a dongle.
Any more? For any more? Well, I think it's just to say thank you very much to Ian for a very interesting presentation.
Thank you.
Thank you. Yes, and I think it highlights the technologies that are available to us to experiment and play with constructing and designing our own radio systems from kind of modular bricks and blocks, and then logically just connect them together in a structure.
Yeah, it's actually get my teeth back in again. It's actually no different to what went on in the analog world when people were building their own oscillators, building their own filters and PAs. It's just what's on the screen now, and you don't your fingers burn with a solder now.
Yes, it's the glue is now logical glue rather than solder. Good. Okay, small break now while maybe a bit more, half an hour break or so until our next one. We're setting up a Zoom session, and Peter will be giving us an update on AMSAT-DL and their activities. So take a break, take a pause. We've probably got time for coffee, and be back here in about half an hour. Okay.